Hi guys, in today's video, I'm going to show you an extended version of slow clock that I have shown you before. Okay, previously I have shown you on how we're going to create a counter so that we can create a slow clock. Okay, as for today, I'm going to show you more. Okay, let's say if you have a row of LED, how you can change the pattern of the LED by using the slow clock as your input. Okay, that's the important part that we're going to proceed today. Okay, how we're going to do that? Okay, this coding, as you can see, exactly the same one as previous. Okay, exactly the same one, nothing have changed. Okay, if you have look, maybe you have to look first. Okay, about the coding, try to understand. It's quite simple and straightforward. Here I give an input clock and slow clock so that I can observe the timing diagram, how the slow clock going to respond according to the clock. Okay, the clock still the input. Okay, but the idea is we want to create slow clock from the clock itself. Let's say the clock frequency 50 megahertz, so that we can um, uh, divide the frequency what to whatever that we want. So if you want to make it 1 second, so you have to divide to 50 megahertz. The input clock that available on the FPGA board is 50 megahertz. If you want to create 1 second, so you have to divide the clock to 50 megahertz. As simple as that. Okay, now what I'm going to do now, so I'm going to remove the slow clock. The slow clock I want to use as a register. Okay, the slow clock is no longer the output because previously I just want to see the wave pattern. Okay, now I want to see the LED pattern. Let's say in the FPGA board, I have 8 LEDs, right? So now I want to assign a different pattern to a row of LED. Okay, let me proceed. Let's say, okay, the out, okay, clock is the input, out is the pattern that I want to assign to the LED. Okay, so input is the clock, register, output, okay, supposed to be out. Okay, then integer I want to create another integer a, and now the register will be the slow clock. Okay, if you assign integer I a, it's going to take 32 bits. If you register, it's going to take whatever the value. Let's say for the sake of example, going to be 100 because slow clock is going to be 100, right? Clock 100, right? So I don't want to use a lot of memory. I want to use a very precise memory. So I just want to call the slow clock as a register. I assign register. Okay. So initial. So what you want to do here? Initial block here. I want to clear I, clear slow clock, and also I want to clear A, make it 0, everything properly, easy, much better. And also out, let's say out also make it 0. Okay, I don't want any value at the beginning to the LED. Okay, so I already assigned the, okay, begin begin beginning value, y values, then later you will know. Okay, because we have 8 LEDs to the 8 LEDs. Okay, so even though you assign 0, 0 going to be 0, 0, 0, 0, 0, 0, 8 times, right? Okay, now we're going to move on to the slow clock. Okay, always a positive slow clock. Here we create a counter. Okay, let I count until 10. Okay, because we want the slow clock supposed to be every time the clock, okay, count to 5. Okay, after that, the slow clock going to turn to 1. Then another 5 is going to be 0. Okay, so divided into 2. Okay, now here we create always a positive edge clock. Begin if I less than 5, slow clock equal to 0. Else if I more than 5 equal to 5, slow clock equal to 1. All right. So you try to analyze, you try to play around with this value and have a look how the timing diagram going to react according to the value that you're going to change here. All right. So now, okay, let me create another new block. Always, okay, always at A is my input now, or positive edge slow clock. See, observe here. Initially here, I use clock as my input. Now, since I want to control the LEDs, I want to use slow clock. Okay, slow clock because I want to see, let's say, here I explained to you before, 10 or 5 I'm using. Let's say if I want to use on the block, here I have to change to 100 megahertz, here I have to change to 50 megahertz, so that the LED blink for every 1 second. It's a 1 hertz clock. Okay, okay, now, okay, begin. Now I want to use case statement. Case what? case A. All right, so now what is the A going to be? Start from 0. Okay, let's say 0. Okay, how what is the value that we want to assign to the LED? Out is going to represent the LED, right? LED 8 bit, right? 8 binary 0 0 1 2 3 4 5 6 7 8. This is the first pattern that I want to assign to the LED. Okay, let me copy this line because it's going to be repetitive. So I'm going to paste 2 3 4 5 6 7 8. Okay, I want to have a 8 different patterns, so change to 1 2 3 4 5 6 7 8 different pattern, because here now A representing this integer from 0 to 7, so that I can assign 8 different pattern to the LED. Okay, it's up to you. This is for the sake of example. Let's say if you want to assign another pattern also, should be no problem. Okay, now so that you can see the propagation from one pattern to another pattern. It'll be quite interesting if I can show you in the lab, because we can directly implement this code to the FPGA board. But unfortunately, since of the PKP, we cannot go to the lab, so now I have to show you from the simulation itself. Okay, don't forget, every time case you must have a default whatever value that you want to assign. If none of the combination take place here, so let's say I want to assign 8, because here going to be all 0 binary 1 2 3 4 5 6 7 8. That's all. Okay, then end case. Okay, then begin must have an end. All right, so that's all. Is it finished yet? No, because of what? A here, okay, A or positive H clock. How does A know at this particular line here is going to stay here how long? So that now you must create another always loop, so that the A can propagate from one state to another state. This is like a state. Okay, this is the first state. Previously you have created a state machine, right? So 0 going to be one state, this first going to be another state, and so on. So this is the state. So how A going to propagate from state 0 to state 1? Okay, you don't know how long it's going to stay in that particular one state, so that we need to create an always block. Always at, okay, positive uh, post h sclk. Okay, now what I want to do, I want to create a counter for the A. So if A equal to 8, okay, A going to be 0, else 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 A equal to A plus 1. So now A going to keep calculate until it going to keep count until 8. So after that, if equal to 8, A becomes 0. Then after that, it's going to keep continue counting again. Okay, and so that from this particular block here, you know, okay, A know that you have to count until 8, then become 0. Count until 8, then become 0. How long? How fast going to calculate count according to the slow clock. Every time we have a positive slow clock, then A will turn from 0 to 1. Every time we have a positive H clock, the A will turn from 1 to 2, and so on until 8. Okay, this is quite interesting. Try to observe and see. This is like some kind of a practical implementation on the board that we can do. Okay, then okay, now our task is to create. I'm going to show some extra on the test bench as well. How we're going to see, if you look carefully, we only have clock and out, right? How are we going to observe a slow clock? Okay, I'm going to show you in this particular example. So now create one test bench file first. Let's say test bench, I have many test bench, so let's say test bench 4. Next, finish. Okay, the inputs here clock, right? So always only create one account of, or a loop for the clock. So I can assign forever loop. Okay, let it keep continuously looping from 0 1 0 1 0 1. Okay, clock. So you're going to toggle from 0 to 1 0 to 1 0 to 1. Okay, so uh, clock become, okay, going to toggle, right? So save that file, click this one. Now I'm saying we can maybe we can check first whether there are any error on my coding. Do you want to say yes? Oh, fortunately, no error. Okay, then click on the test bench and simulate behavior model. Hopefully everything is fine. Is there any error or not? We're going to see after this. There's some error. Okay, no problem. Okay, cannot propagate. It doesn't know z mean. Okay, you don't know whether what state is it. So no problem with that. But what we can do now, let me try to uh, find out where is the problem. So okay, let me try to add I, A, and slow clock as well into my timing diagram. Add to wave. Then okay, I'm going to relaunch. Do you want to save? No. Okay, there's the interesting, but okay, we can see here the slow clock is propagating properly. Okay, let me try to okay, both of these change to radix, unsigned decimal. Okay, the A going to count from 0 until 8. See, then become 0 back. Okay, so it's counting from 0 until 8. So if you want only 8, right, so it can be 0 until 7, right? 0 until 7. Okay, change the value. This is how you do the correction for the programming. You have to see, observe the timing diagram. Once you find any problem here, then you're going to rectify back. Okay, here same goes here, 0 until 10, right? Because you want 0 until 9, so that it become a 5 right? Because 0 until 9 we have 10 different state, right? So change it. See, when you observe on the timing diagram, you know where you can do the correction on your coding. This is how you learn. Okay, we have to observe. After that, you have find out where is the error, then go and correct it. Okay, do it around to exit. Yes. No. Okay, now I want to change a bit my coding. Go to my coding. So this value here going to be 9, no longer 10, 9. So the value here is supposed to be what? Only 7. 7. Yeah, there you go. So now we see there's a problem with the out, right? Oh, okay, there you go. I didn't put the, see, this kind of silly mistake can take place. Aha. Now this is how you learn programming. There you go. This is the real world. Welcome to real world, guys. This is how we write the coding. Okay, save the file. Okay, simulate behavior. I think should be fine now. Da, 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 da. There you go. We don't have to. Okay, now I want to add. Okay, initial. Okay, I want to add I, A, and slow clock to my timing diagram. Okay, add to wave. Okay, now I'm going to relaunch again. Okay, do you want to save? No. There you go. So change to A and I into unsigned decimal, much easier for you. Unsigned decimal. Okay, can you see it? Okay, much. Okay, now try to interpret the timing diagram here. You can see what's going on here. We start from the beginning, in the beginning. Okay, you can see the pattern here. See the output now, the out here representing our pattern for the LED, right? So the pattern of the LED propagating from 1 until to 1 1, and then after that 1 1 1, according to what you can see here, the slow clock. The slow clock here, the time period. Okay, at every positive edge, okay, at every positive edge of the slow clock, okay, it's going to change the value, or the LED going to change the pattern. Okay, after that, you're going to retain on the 0. Then after that, on the next positive edge of the slow clock, you're going to change to another pattern, and so on and so forth. So you can see here, the A value, A is going to calculate according to the positive edge. See, this particular duration here, from here until here. So according to the slow clock, right? So A only going to change according to the slow clock. So the slow clock A, we have assigned A is like a state, from A is like propagating from one state to another state, right? So now A, the output also going to change from one state to another state. So every state also we can execute our different type of output, right? A different pattern of the output, right? So we can see. So this is the line for the clock. So clock here is the line for the slow clock. Here where the A going to change according to the slow clock now, no longer clock. Then after that, you're going to get the output pattern. I hope this is something interesting that you can learn something new. At the same time, I've shown you how we can rectify or correct our coding. So it's not necessary when you write, you're going to get the right coding. No, same goes to me. I have to look back whether I have done some error, what's going on here. This is the real life. This is how you're going to write the coding in the real life. Okay? Even the expert also doesn't matter how expert are you. This is the real life. You're going to see some error. You're going to come back to the timing diagram. You're going to run again. See? come and forth. So you're going to keep repeating the same thing. You're going to come to the coding and say, is there any error or not? Sometimes it's working, sometimes it's not going to work. So you're going to figure out until you find the expected output that you want. All right. This is the real life. I'm showing you the real life. Okay. Hope it will be helpful for you. Next, I'm going to upload for the project. Okay. Okay. What we can assign here? Actually, we can assign another file, okay, where you can do the mapping the led from the port here to the physical port of the on the board. I'm going to show you next, and try to have a look first at this coding, and then maybe I can show you next how we're going to do the mapping, the user constraint file on the data sheet that we have, or they already provide all the pin number, so we can assign the pin number to the each one of the led that we assign here as the output here. All right. Hope it's helpful. Thank you so much, guys. See you soon.